Hello guys, welcome back to my YouTube channel. This is fifth video of our series of nuclear physics. We are discussing the chapter nuclear structure and basic properties of nuclei. Here in this video, we will discuss the topic binding energy and nuclear mass. Under this topic, we will consider the definition of binding energy. Then we will define mass defect. After that, we will consider the definition of binding energy in terms of mass defect, means we will see the relationship between binding energy and mass defect. Then we will derive an expression for binding energy, and in the last we will define binding energy per nucleon. So first question arises in our mind that what is the objective of learning binding energy? Binding energy is needed to learn to find out binding energy per nucleon, which is a very important quantity because it accounts for the stability of nucleus. So to compare the stability of nucleus, we need binding energy per nucleon, and to find out the binding energy per nucleon, we need binding energy. So we need to learn binding energy. So let us move to our first topic, that is binding energy. Energy required to decompose nucleus into its constituent nucleons is called binding energy. Let us explain this definition in detail so that you can understand it well. For this, let us consider we have two particles. These particles have some attractive force in between them. This attractive force may be gravitational force or electrostatic force. If we want to separate these particles apart, we have to do work against this attractive force, and to do that work, we require some energy. Similarly, in the nucleus, we have nucleons which are bind together with the force called nuclear force. This nuclear force is attractive in nature and it is a short range force. Short range force means nuclear force acts only when the distance between the nucleons is of the order of 10 raised to the power minus 15 meter, which is the size of nucleus. Means nuclear force acts only when nucleons are inside the nucleus. If distance between nucleons is more than this order, then nuclear force will not work. So this is the meaning of short range force. If we want to have these nucleons independently, means we want to decompose this nucleus and want to have these nucleons separately such that these no nucleons have force due to any other nucleons. So in this situation, these nucleons are called independent nucleons. If we want to have these nucleons independently, then we have to do work against this nuclear force, and to do that work we require some energy, and that required energy is called binding energy. So energy needed to decompose this nucleus to its constituent nucleons is called binding energy. So this was the definition of binding energy. Let us move to our next topic, that is definition of mass defect. Mass defect is the difference between sum of rest masses of nucleons and actual rest mass of nucleus is called mass defect. Let us explain this in detail so that you can understand the mass defect clearly. Let us say in first situation we have nucleons which are independent. Independent nucleons means no nucleon have force due to any other nucleons. Let us say we have 3 protons and 3 neutrons. And all the 3 protons have equal mass equal to mp, and all the 3 neutrons have equal mass equal to mn. These are rest masses of nucleons. We are considering the rest masses of nucleons. Then sum of rest masses of all the nucleons is 3 times Mp plus 3 times Mn. In second situation, these nucleons are brought together to form a nucleus. In this situation, they are bind with nuclear force. Overall, this nucleus has mass Mn. So it was found that actual rest mass of nucleus is less than the sum of rest masses of all the nucleons. We can say that when nucleons are brought together to form a nucleus, some mass get disappeared. So the difference between sum of rest masses of all the nucleons and actual rest mass of nucleus is called disappearing mass or mass defect. So mass defect is the sum of rest masses of nucleons, which is 3Mp plus 3Mn minus actual rest mass of nucleus. Difference between sum of rest masses of all the nucleons and actual rest mass of nucleus is called mass defect. It is also called disappearing mass. Disappearing mass, and it is denoted by delta M. Let us take example of deuteron to clear it. Let us take example of deuteron. Deuteron is nucleus of isotope of hydrogen having mass number 2 and atomic number 1. This is deuterium isotope, and deuteron is nucleus of deuterium. So this nucleus will contain one proton and one neutron. Proton have mass equal to Mp and neutron have mass equal to Mn. We want to find out the mass defect. For that, we need sum of rest masses of all the nucleons. Sum of rest masses of all the nucleons is equal to Mp plus Mn. Mp is 1.0073 atomic mass unit and mass of neutron is 1.0087 atomic mass unit. Then sum of rest masses of all the nucleons is 1.0073 plus 1.0087. It will come out to be 2.000160 when we add it, 2.0160 atomic mass unit. And actual rest mass of deuteron, actual rest mass of deuteron will be 2.0136 atomic mass unit. Then mass defect will be equal to Mp plus Mn, sum of rest masses of all the nucleons minus actual rest mass of nucleus. 2.0160 minus 2.0136. When we subtract it, we will get 0.0024 atomic mass unit. So this is the mass defect in case of deuteron. Let us move to our third topic, that is the definition of binding energy in terms of mass defect. As I have already told that some mass get disappeared when nucleons are brought together to form a nucleus. Where this disappeared mass goes, this disappeared mass gets converted into binding energy. So energy equivalent to disappeared mass is called binding energy. And by using Einstein formula, we can get the binding energy if we have given with mass defect. So we multiply C square with mass defect to get binding energy. This is the relationship between binding energy and mass defect. Let us derive expression of binding energy. For this, we have to consider a nucleus and we will find mass defect for this nucleus. Then we will multiply C square with mass defect to get the binding energy of this nucleus. Let us derive this. Consider a nucleus of element X having mass number A and atomic number Z. This will contain Z protons and A minus Z neutrons. We need number of nucleons here to find out the sum of rest masses of nucleons. So Z protons and proton have mass equal to mp and neutron have mass equal to mn. Then sum of rest masses of all the nucleons, sum of rest masses of all the nucleons is equal to Z times mp plus A minus Z times mn. So this is the sum of rest masses of all the nucleons. And now actual rest mass of nucleus. We need actual rest mass of nucleus also to find out mass defect of nucleus of this element. Let us denote it with Mn AZX. Then mass defect will be sum of rest masses of all the nucleons, that is ZMP plus A minus ZMN minus actual rest mass of nucleus of this element. This is the mass defect. Then binding energy will be delta mc square. Putting the value of delta m from here, ZMP plus A minus Z times mass of neutron minus nuclear mass of this element into C square. This is the expression of binding energy in terms of nuclear mass. Here we are not considering the mass of Z electron. If we add and subtract mass of Z electrons also, we can find out the binding energy expression in terms of atomic mass. Let us do it. Add and subtract mass of Z electron, which is ZMe. AB is equal to ZMP plus ZMe plus A minus ZMN. Here we have added mass of Z electron. Now we will subtract mass of Z electron. Z times Me into C square. Taking Z common, we get MP plus Me in the bracket plus A minus Z mass of neutron, and taking minus sign outside the bracket, we will get Mn A Z X plus, here plus sign will become, taking the curly bracket here, and element having one proton and one electron is hydrogen. So this will become mass of hydrogen. So this in the term in bracket will become mass of hydrogen plus A minus Z mass of neutron, and this term in this bracket will become atomic mass of this element because we have added the mass of Z electron which are moving in the periphery of this atom. So this will become atomic mass of this element. C square. This is the second expression. So this expression is expression of binding energy in terms of atomic mass. Let us move to our last topic, that is binding energy per nucleon. Binding energy per nucleon, which is a very important quantity because we have to calculate this quantity to find out the stability of nucleus. It is energy required to extract one nucleon from the nucleus. Extract one nucleon. It is a ratio of binding energy to the total number of nucleons, which are represented by mass number. So average binding energy per nucleon can be calculated by dividing EB by A. So let us see how we can calculate average binding energy using binding energy, average binding energy per nucleon. Average binding energy per nucleon is EB by A. We will put the value of EB from this second expression. Then average binding energy per nucleon will be equal to Z times mass of hydrogen plus A minus Z mass of neutron minus atomic mass of this element into C square by A. So this is the average binding energy per nucleon in terms of atomic mass. So this was all about the lecture, and next topic, that is binding energy curve, we will see in the next video. Thank you.